Yeah, thank you very much for the introduction, and thank you very much, Ningning and Professor Zhang, for inviting me to giving this talk. It's going to be about the applications of physics-informed neural networks to deep-seated landslides. So it's a little bit long, and I don't have a lot of time, so I'm going to start straight away. I will tell you a little bit about the institute very quickly, not the bio, you just heard it, so I won't say anything. Then I will give a brief explanations of what type of landslides is it that we want to model here. A little bit about physics-informed neural networks and how we applied it to this particular problem. Okay. So yeah, you heard the bio. I worked in industry for a number of years before I became an academic in the UK, and then through some twisted turns in life, I went through Valencia, and then I ended up here in Aachen, where I am the professor of geotechnical engineering since 2020. So these are our institute at the moment. Like you can see, there's we have a number of postdocs, 4 or 5 postdocs, and a number of PhD students. And we're working in many topics. One of the main ones is ground-robot interaction. We're also working in soil fluid structure dynamics, new technologies, particular AI, pins, what we're going to talk today, but also sensor technology, temperature in the ground. What I call temperature in the ground, I mean frozen soils and geothermal, geogrid and geotextiles, and we also do a lot of work on rock mechanics. Yeah. Okay, so just a little bit so you get to know us a little bit more. Let's start with the landslides. So this type of landslides that we are talking about are deep-seated landslides, typically where you are reactivating an existing or historical landslides. They have a peculiarity that they all have a shear band, which is where it has been actually created in the past, like I said, or was existing through the geology, and that this is where the failure mechanism happens. What you can see here is Beyond in Italy. That is a very well-known case study that has been used multiple times in the literature to study landslides and also run-out distances, mechanisms, etc. Yeah, you can see here is that this was a very large landslides, and there was it was monitored significantly because this was part of a reservoir, so it was in the sides of a newly built reservoir. And then when they started to fill it up, they saw that the landslides was activating, it was moving. So they installed a lot of monitoring, and then they started to see what was happening and filling it up, reducing the level, etc., until it tragically collapsed. And this is what I wanted to show you. So this is the geology, more or less. You don't have to look at the details. The most important detail here is this thin shear band that is happening where the failure mechanism happened. And that was a new slide that was activated along or very close to what the old slide failure surface was. Yeah. It collapsed on this date, and it mobilized this amount, or 270 million cubic meters of rock mass with a thickness of 150 meters. And unfortunately, it caused 2,000 deaths because it created a tsunami that overtopped the reservoir, and then it flushed downstream, hitting a nearby village. That's yeah, where a lot of lives were lost, unfortunately. So here you can see some of the features of these landslides along the shear zone and where this shear band happened. Yeah, I'm not going to go into this here. You can read it later if you want when you look at this at the presentation again. But remember, we're looking at these thin shear bands. This was a landslide that was accelerated very quickly, and it reached here. This is a modeling that was done with using MPM, which predicted about 20. In reality, it reached probably higher velocities. Of course, nobody was monitoring the velocity, but this was kind of estimated, and it displays the long distance. Yeah, the sliding mass moved to over 300 meters from its original position, and this is what caused this. The combination of this high energy from the high velocities, the large displacements, caused this large tsunami that I mentioned earlier. And then when they started to study, and this was one of the seminal papers from, well, Bebeakis, but Professor Bartoulakis, they started to see how this landslides, and this is a feature of all of these type of landslides, is that they kind of go slowly. They start moving slowly, slowly, slowly. This was the original, yeah, what they think could have been the original. And then then they accelerate super quickly and reach these high velocities that that I showed earlier. This is a typical feature of this type of landslides. And what Professor Bartoulakis and co realized is that this also was related to an increase in temperature because of the friction, of course, and that this increase in temperature changed the strength of the material. In this case, the shear band was composed of some clay material, which increased the pore water pressures, which reduced the effective stresses, which it becomes like a self-feeding mechanism in which the more the quickly it slides, the more temperature it generates, the more it reduces the strength, and the more the slide accelerates. So this is the kind of the mechanism, yeah. A little bit of NPM modeling to show what was happening. So they started to feel the reservoir on this side, and this reduced the effective stresses enough on what was already a very low factor of safety, if we want to talk in terms of factor of safety, that then trigger the landslide. And remember, this is a self-feeding mechanism. Once it starts sliding, it increases temperature, reduces shear strength, and the whole thing accelerates. So yeah, you can see some of the displacements, and this was able to model very nicely the landslide, so 350, and some of the other features and the temperatures that were reached here. So the temperatures of about 50 degrees along the shear band. This is the important bit, yeah. The important bit is that there's a shear band and there is temperature that is created. Why? Because if this is the case, and temperature is something that is could help us understand that things are accelerating, then if we monitor it, then we could potentially predict the occurrence of these events. And this is what we are going to try to do here today. Just another slide showing the very quick acceleration of the landslides once it reached a certain level and it failed. And this was, of course, related to the filling and reduction of the reservoir level. But this was just one case study. There's two other case studies that I'm going to very quickly introduce that are very similar in features, different volumes, different geologies, different depths of mobilized material, but sharing this feature that there is a pre-existing or potentially pre-existing failure surface with a shear band, thin shear band, that causes this to happen. And this is the example of Mud Creek in California. You can read more examples here, but what happened here was very similar to what happened in Bayonne. So this is an analysis. There were no measurements in Mud Creek, but you can see the velocity of the landslides, or how it shoots out, you know, very quickly and high up, yeah, when it fails. Okay. So very rapid landslides once they get mobilized. Another one that is in Shuping is called a Shuping landslide, and this is in the basin where the Three Gorges Dam has been built. And this luckily has not failed, and we hope that it will not fail. But it shares similar features to the other two landslides, and this is kind of at a starting phase of the development. Yeah. So you have also an ancient or an old landslide failure surface here. And what it is believed by what has been monitored here is that this is being reactivated now by possibly the construction of the Three Gorges Dam, possibly by other mechanisms. Right. So once they observed this, then they started to Bartoulakis and company, and Carolina, who was a postdoc here as well and has worked with Manolis Bebeakis in Duke University. They tried to develop a model that could enable them to predict the behavior of these landslides and predict how they will behave. So they use a combination of a two-wedge mechanism that was very representative of what happened on site, and an infinite landslide model with a shear band here that you can see, where you have a velocity to there's the thickness of the shear band, shear stress along the failing surface, and a normal stress, and a temperature here. Yeah. that is caused through the friction. Yeah. I don't have time to go through all the details, but eventually, if you go through the development of this this model, you come out is with this partial differential equation, in which you have temperature, non-dimensionalized theta, time, and the thickness of the landslides, and then critically what is called Grunfus number. This Grunfus number is a bifurcation parameter that they stipulated, they presented, and what they realize is that when this Grunfus number reaches values of around 0.88, the landslide fails, and then it goes into an unstoppable mechanism in which you cannot stop it anymore. Yeah, so critically, if you can calculate the Grunfus number of these landslides, then you can predict or you can see whether it is close to failure or not. And of course, this is related also to temperature, to this theta here. You may be thinking, why are we going to use neural networks to solve this equation that doesn't seem particularly difficult? It is very difficult because this is a difficult number that includes a lot of other parameters here, the shear stress, thickness of the landslide, and others that can potentially change as well during the development of the physical mechanism, and of course M, which also depends on temperature, like you can see here. So it's not straightforward to solve, and this is why we also thought that maybe neural networks can help us solve this problem. So in summary, we have 3 case studies. These are the characteristics: large volumes of material mobilized and thicknesses, varying thicknesses with different potential causes or activation mechanisms. So what we're going to see essentially covers various conditions. Now, let's go to PINs, Physicals Informed Neural Networks. And this is probably one of the seminal papers on this, which was done by Professor Karniadakis in Brown University and company. And essentially, what you want to do is solve these partial differential equations using neural networks. Yeah. So typically, these PDEs you can solve with other numerical approaches, boundary value problems. But in this case, what we're trying to do is using neural networks. That's one implementation. The implementation that we're using is the one done by Esan Hi-Hat and Raul Fuentes from MIT, who actually are working with us on this topic, not in landslides, but on something different, using pins. And this is a very convenient implementation because it's using TensorFlow and Keras. It's all open source, and you can access it whenever you want, and it's a very nice framework. Right, how does this work? Well, in this case, in typical neural networks, what you have is an input and an output. An input is approached through a number of weights and biases that are multiplying each number of neurons that are in each of these layers. So what you can see here is the hidden layers of a neural network. And then what you want to do, of course, is from these inputs, calculate the outputs. And typically, you will measure the error, compare these two, and keep iterating until your error or your output reaches an error that is tolerable, yeah, within a certain tolerance of what you would like to achieve. What are we doing with pins? With pins, we are doing the same, but now we are including the partial differential equation in the loss function. So when we calculate the error, we don't only calculate the input to output difference, but we also estimate the partial differential equations. And this is where we introduce the physics. So we are not only using data, we are introducing the physics of the problem, but minimizing our estimates to predict this PDE. And this is in a nutshell, more or less how it works. So this is what we did, of course. We introduced the PDE here in the mean square error. So every time you do an epoch, an iteration, then you calculate your loss function here, which could be only data, it could be only the PDEs. There are different approaches, it doesn't matter now. And then with a certain algorithm, you keep updating your parameters, and they get an activation function, which I'm going to talk about very briefly. And then you backpropagate to start again, going through the network, trying to create better approximations. So the end of the problem is this: we have a governing equation, a loss function that is defined in this case by the loss of the differential equation and the initial condition. We don't have boundary conditions in this case. In some cases, you will have boundary conditions here, and they will be incorporated into total loss function of the PDE. this is calculated, and you calculate it in a very similar way. So you do the estimate, and then you compare it to the to what you're getting, and the initial condition the same, and then you estimate it. Okay, so what results did we get? So first, just I wanted to point out that the importance of normalizing the values. And this happens for most of the problems that you will ever try to solve using pins, especially when you have variables, input parameters or output parameters that have very different numbers. So numbers, typically when you have permeabilities 10 to the -8, or other parameters that are in very wide ranges, this introduces also numerically in traditional numerical models, but very importantly here in pins, introduces significant problems, and you need to normalize all of your data. This is very important, and this we realized that very early on, and we were able to then train the network a little bit better. And you can see here some of the differences of you can get from training in the same case. We are training now in one of the cases and comparing in the same case just to test the effect of non-normalized values versus normalized values. And you can see clearly here what the effect is. Yeah, right. So that's just a little thing to understand. And then what we started to do is try to train on different cases and test on other cases. So Bio and MudCreek, they share some similar features. So we used the data of Bio to train the PDE and the network, and we tested on MudCreek, and we got reasonable results like what you can see here. But these are similar landslides in the case that in the sense that they both failed. So they had this ramp, and therefore they share common features, while also the cycles that we were using to train are very similar. By the way, this is temperature here on the left, yeah, and this is time on the x-axis. However, when you train on Bio and test on Shuping, which is a landslide that has not failed, and what you can see here is the real data of Shuping, then the results are catastrophic. Yeah, it doesn't work. We did a number of combinations. So MudCreek and Bio were good friends. They always compare well, but every time you include the Shuping, the thing didn't work. Even including Shuping as the training and testing on Bio or MudCreek, of course, Shuping does not have this shooting up stage, and therefore it was not capturing that very well, neither in Bio nor in MudCreek. So we then realized that we needed something else. Okay, even training Shuping and testing on Shuping landslide was not enough. Then we also tried different combinations, so training in 2 landslides and testing on the 3rd, and this also did not yield good results, especially when we were considering Shuping, like for instance what you can see here in the testing. Yeah, so we needed something else. What did we do? We used synthetic data. So we created our own synthetic data, and this was approached numerically from a paper from Kinato and Bardulakis in 2007 or 8, I can't remember. And we created our own data. So we created our own Grunfus number as a function of time using this equation, in which in this case C dictates more or less the number of cycles that you get, which in this case could be seasons, so with different precipitations or precipitations seasons, and then this will create this kind of wavy profile. And then when we did this, then we trained and we tested on the data, we started to get better results. But then, of course, what we wanted to do is see how it worked on the real case studies. And then some for information, as activation function, we use a tangent hyperbolic tangent. If you're not familiar with this type of pins or approaches, it may be worth telling you that it is good to use an activation function that is derivable, that you can derive at the same order of your PDE. Yeah. Otherwise, it can also cause problems. So if you have a second order derivative, you should use an activation function that has a second derivative as well. In this case, we use a fully batch approach as well, 5,000 epochs. And these are some of the hyperparameters that we fine-tuned by eye, essentially. So trial and error with this learning rate. And then what was critical, and this is also a question that arises when you use neural networks in general, but also in pins, of course, is how many layers, how many neurons you use, yeah? And we face the same question, of course, that everybody else, because there's no theoretical approach to this. And in general, it's done by trial and error. So what we try to do is come up with a more systematic way of estimating what number of layers and what number of neurons we were going to use. Well, this is just to show that it started to then train very well. So we reach two types of architectures with 3 layers and 20 neurons, and 4 layers and 16 neurons that were giving us a very good training for both the PDE, but also for the temperature and the total, which is, of course, the addition of both. And also something that you may want to consider if you're working on something similar is that every time you make an estimate or you run your network, you train your network, you're going to get a slightly different results, which translate into different standard deviations of the different results. As you can see here, it is 5 realizations. And this is, of course, to complicate things, not something that you can estimate saying, okay, if I have 3 layers and 20 neurons, this is the standard deviation I'm going to get. And if it's 4 and 10, then this is standard. No, you don't know in advance, or at least we don't know. If somebody knows how to estimate that, please let us know. We didn't know, but this is, of course, something that you don't want. You want a very robust architecture that gives you low or high confidence bounds. And based on this and everything else, then what we did is come up with this scheme in which, of course, we want to minimize the absolute error that we're getting. So we want to increase the accuracy. Yeah, but we also want to have a very stable architecture that produces the same results every time. So the standard deviation of what I show you is also very low. And then, of course, what we were also doing, and you always have to do, is make sure that your network is not overfitting. Yeah, so we tested that. So with these 3 criteria, that it will not overfit, that will give us an accuracy that was adequate to us, and that it was repeatable and stable. This is how we ended up coming up with these 2 architectures that you saw earlier: 4 layers, 60 neurons, 3 layers, 20 neurons, for all 3 cases that are color-coded here. Yeah. So eventually, this is how we decided that these are the number of layers and the number of neurons that we were going to use. And then we tested this with the hyperparameters that I showed you earlier. And then all of a sudden, we started to get very nice results. So with synthetic data, of course, it was very nice, but also it was getting very nice prediction of beyond, critically predicting the shoot up very nicely. The same in Mud Creek here. And in Shooping, getting very nice, the waviness, if you want, or the different cycles, even though we were not able yet to capture this peak in temperature at this particular time. Yeah. So, of course, we may improve the synthetic data and add more synthetic data or more case studies, and then the predictions will get better, or at least this is the theory. Okay. So, just a summary. These pins are, I think, very promising tools for solving PDEs without using the traditional numerical approaches, especially for complex PDEs. I think it offers a lot of opportunities. This is just our experience. I want to share it with you. I apologize, like I said, if some of you are experts in this as well, but normalizing the data is very important. Synthetic data can help you when the amount of case studies that you have is not sufficient to achieve good description of the problem. The network architecture is very important for many reasons, of course. But don't rely only on the error that you're getting. That is just one aspect. Yeah, I think stability is also important, and this should be considered. And this is maybe using a similar approach to what we show you could be interesting. And then we have achieved what I think is a good generalization for different landslides. Remember that Shooping, it's very different landslides where the Grundfos numbers are only 0.08, whereas in Bayonne and Mud Creek, they reach the critical 0.88. So Shooping is kind of developing. Hopefully we'll never reach there. But then with synthetic data and other data, you can get very good results. So now we are working on writing a paper and then thinking that if this is the case, then we have a very good model that we can keep feeding and use in combination with temperature prediction on site to estimate whether a landslide is going to fail or not. Just a couple of acknowledgements to Ahmad, who is working with this and has done all the work, Carolina, who is a former postdoc, and some of the other guys at the Institute has been working with pins with us during this time. Thank you very much for your attention.